Hi, my name is Charan. I would like to explain a design of continuous beam from VIT University, Chennai. First introduction. Beams are made continuous over the supports to increase structural integrity in regions with high seismic risks. Continuous beams and frames are preferred in buildings and bridges. A continuous beam is statically indeterminate structure. The diagrams are shown spans and intermediate spans, and in two diagrams, first diagram A diagram is shown the building structures. What are the beams we are using? One example it shows, and say B diagram continuous beam in a bridges. How we use in continuous beam in bridges? It shows in it present the in diagrams in between. Design of example of continuous beam. We take one problem. Design of continuous reinforced concrete beam of rectangular section to support a dead load of 10 kilonewtons and live load 12 kilonewton per meter over 3 span of 6 meters each. The ends are simply supported. Adopt M20 grade concrete and FE 415 high yield strength bars. Sketch the first we take the data. Effective span is 6 meters, dead load 10 kilonewton meter, live load 12 kilonewton meter, concrete M20 grade and steel FE 415 high yield strength bars. Second step, cross sectional dimensions. As the continuous beam supports heavy loads, so span by depth ratio is assumed as 10. Effective depth is D is equal span by 10 is equal, if we take the effective span 6 meters, then in millimeters 6000 meter by 6000 millimeter by 10 is equal to 600 This is the effective depth. Adopt effective depth is 600 overall depth is 650 and width is 300 Cover to tension steel is 50 next we calculate the loads. Self weight of the beam is equal to 0.3 into 0.65 into 25. 25 is the self weight of concrete, reinforced concrete, so we take the 25 as a into area, 25 into area. The self weight of the beam is 4.875 kilonewton per meter. Dead load 10 kilonewton per meter. Finishes 0.125 kilonewton per meter. Total dead load is G. We consider as a G 15 kilonewton per meter. Live load is 12 kilonewton per meter. Next step is bending moment and shear forces. Referring to the bending moment and shear forces coefficients, negative bending moment at interior supports is computed as mu negative is equal to 1.5 into GL square by 10 plus QL square by 9 is equal to 1.5 into 15 into 6 square by 10 into 12 into 6 square by 9 is equal to 153 kilonewton per meter. This is the negative bending moment at interior supports. Positive bending moment and entire span is computed as mu positive moment is 1.5 GL square by 12 plus QL square by 10 is the formula. Then we calculated by for the calculation we get the 132.3 kilonewton per mm. Maximum shear force at the support section is given by VU is equal 0.6 L into G plus Q into 1.5. We calculated by the calculation we get the shear force at the supports of section is 145.8 kilonewtons. Next step is limiting moment of resistance. Mu limit is equal to 0.138 FCK BD square. FCK BD values are we taken, then we get the limiting moment of resistance 298 kN per meter. Since mu less than mu limit, the section is under reinforced. Main reinforcements we calculated after concluding completion of before calculations. Mu is the 0.887 Fy AST into D into 1 minus AST Fy by BD into FCK. We take the values Fy AST D Fy BD FCK values, then we get the AST is 780 mm square. Using 2 bars of 25 mm diameter on the tension side, AST we get 982 mm square at the supports. For the positive bending moment, the area of steel required is 675 mm square. Hence, provide 2 bars of 22 mm diameter on the tension face at the midspan. Then for the next step is shear reinforcement on continuous beam. Tau V is equal to Vu by BD. Vu is 145.8 into 10 power 3 by BD is 300 into 600 mm is equal to, we get the tau V is equal to 0.81 Newton per mm square. PT is equal to 100 AST by BD. We get the value 0.54 as per referable table number 19 IS 456. The permissible shear stress in concrete as tau C is 0.49 Newton per mm square. Since tau V greater than tau C, shear reinforcements are to be designed and to resist the balance shear computed as VUS is equal to 145.8 minus 0.49 into 300 into 600 into 10 power minus 3. We get the value 57.6 kN. Using 8 mm diameter 2-legged stirrups, the spacing near supports is SV is equal to 0.87 Fy AST D by VUS. We know the Fy ASV VUS D values. Then we substitute those values. We get the 376 mm. Adopt 8 mm diameter 2-legged stirrups at 300 mm entire throughout the beam. We get the spacing of stirrups, 2-legged stirrups. Then we calculate the check for deflection control. PT is 0.54 and modification factor KT is equal to 1.2. Neglecting the hanger bars, KC is equal to 1 and KT is equal to 1.0. Then we have formula. Formula is L by D max is equal to L by D basic into KT into KC into KF. Then we substitute those values. We get the 31 and L by D actual is the another formula 6000 by 600 is equal to 10 less than 31. We get the value. After completion of design of continuous beam, we draw the reinforcement details of the continuous beam. This is the beam with 3 spans and 4 supporteds. The horizontal reinforcement is 2 bars 25 mm and the vertical reinforcement is 2 bars 22 mm. Each span has 6 meters. Each span is 6 meters. The beam dimension is width is 300 and effective depth is 600 and overall depth is 650. The below diagram shows the reinforcement details at section Y in Y direction, in section XX direction. This is the overall design procedure of continuous beam. Thank you for giving this opportunity.